Now we saw that when the diode conducts, that is when the anode voltage is greater than the cathode voltage, the diode starts conducting, means that allows the current to flow. So if this is a diode, and if this the anode voltage is greater than the cathode voltage, that is the anode voltage is greater than the cathode voltage, it will allow the current to flow. Fine. So when this is the condition, so it will act like there don't exist any diode in the circuit. What I mean by this, suppose I have a circuit here, okay, and if I connect a diode like this, then obviously the anode voltage is higher than the cathode voltage here, and the diode will allow the current to pass. So from the circuit perspective, it will act like there don't exist any diode at all, because there is no changes in the current here. The current will be 10 amp, okay, the current will be 10 amps, and it will act like, from the circuit perspective, it will act like there don't exist any diode. Okay, so this was the case of ideal diode. But practically what happens is that whenever the diode is forward biased, a small voltage is dropped across the diode. What I means, suppose this is the diode A is key. Obviously let's consider that the anode voltage is greater than cathode voltage, current is flowing, suppose ID. So here what will happen, a small voltage will be dropped, approximately 0.7 volts. Okay, so there will be a small voltage drop inside the diode, and for the germanium diode this voltage drop will be approximately 0.2 volts, and for silicon diodes it will be approximately 0.7 volt. Okay, so this much voltage will be dropped across the diode. So let's analyze the diode now. So to analyze that, what you do is that you, this voltage drop, you shift it just before the diode. Okay, this is, suppose this is 0.7 volt. Okay, so what will be the condition for the diode to conduct? So here previously when we didn't consider this 0.7 volt, the condition was the anode voltage should be greater than cathode voltage. Okay, anode voltage. But now when there is a 0.7 volts drop, so let's assume a point here, so denote is at x. So now the condition will be for the diode to conduct, Vx should be greater than Vk. Okay, this is now the new condition for the diode to conduct. So what is Vx? Vx is equal to Va minus 0.7, okay, greater than Vk. So this basically means Va must be greater than 0.7 volt. Okay, so this is the new conditions for the diode to conduct. Okay, so this is the new condition for the diode to conduct. Means now previously Va minus Vk, if it was greater than 0 volt, then the diode will conduct. But when we consider this voltage drop, now the voltage across the diode, that is the Va minus Vk, it should be greater than 0.7 volt. So if I consider this case, so how the Vi characteristics will look like now? Now the VI characteristic will VI characteristics considering voltage drop in diode. Okay, so considering this condition, now the VI characteristic will look like this thing here, like this. Okay, this is a straight line here, this is also a straight line, and this is will be like 0.7 volt. Fine. So now when the VD, that is VAK, when the voltage across the diode, that is VAK, is greater than 0.7 volt, then only the diode will conduct. So this is the VI characteristics considering voltage drop in diode. Fine, this is practical case. So in practical diodes, another things needs to be considered, that is the resistance in the diode. So diode also contains a small amount of resistance, so that also we should take into consideration. So if we consider the resistance in a diode, how we can draw the circuit. So here obviously the 0.7 volt drops plus a small resistance here. So now what will be the condition for the diode to conduct? Again, to check this condition, what we can do is that we can shift the voltage drop and the R outside of the diode, and consider this point as X. Now for the diode to conduct, the Vx should be greater than Vk. And what is Vx? Vx is Va minus 0.7 minus, suppose the current I am denoting as ID into R, means the drop here will be ID into R. So this thing should be greater than Vk. Now if I rearrange, it will look like, okay, so this is the new condition considering voltage drop plus the resistance across diode. Okay, new condition for diode to allow current. Okay, so now considering this voltage drop plus the resistance, again how the VI characteristics will look like. So VI characteristic will look like, if I connect 0.7, so this is the VI characteristic considering voltage drop and resistance. This resistance is called the internal resistance of the diode. Okay, so considering the voltage drop and internal resistance of diode. Okay. So why this shape looks like a slope here? Now see, so what was the condition? Greater than 0.7 plus id into r. Now when the id is 0, if I consider a circuit and id is 0, there means the current that is trying to flow through the diode is 0, then vak minus v0, the condition will be 0.7 volt. Okay, so this is the conditions. Now suppose the current okay. Now suppose I've considered a 10 ohm resistance. Okay, so in this condition what will be the current? Current will be 1 ampere. So current will be 1 ampere in this circuit. So va minus vk will be greater than 0.7 plus, let's consider r is equal to 1 ohm. Okay, what will be id into r? It will be 1. This 1.7. So where will be 1.7? 1.7 for id is equal to 1. For id is equal to 0, it was 0.7 id. Suppose now id is equal to 2. How id can be equal to? Suppose if I consider resistance of 5 ohms, then id will be 2. And when id will be 2, what will be? va minus vk will be greater than 0.7 plus 2 into 1, that is 2.7 volts. So 2.7. So as you increase current, this voltage will get shifted here in this direction. So it takes the shape of a slope. So this is the VI characteristics considering the voltage drop and internal resistance of the diode. So just the in practical diodes, just one more thing we need to consider, that is the reverse saturation current. So what is reverse saturation current? So see, in this region the diode is in reverse biased condition. That's why the diode is not allowing the current to flow. This region is in a reverse bias condition, and what we expect during the reverse bias condition, the diode do not allow the current to flow. Basically the current through the diode will be 0 in this reverse bias condition, as evident from this graph. Okay, but what happens is that a small amount of current, a very small amount of current keeps flowing through the diode. Okay, even in during reverse bias condition, this is basically due to the minority charge carriers that is present inside the diode, and because of this minority charge carriers, a small amount of current flows through the diode even when the diode is in reverse bias condition. Okay, and that current is called as the reverse saturation current. Okay, so if I want to consider the reverse saturation current, how the VI characteristics will change? So by considering the VI reverse saturation current, the characteristic will now look like this. Okay, so this is now the VI characteristics of a diode considering the voltage drop, the internal resistance plus the reverse saturation current. So this is means this amount, this is the reverse saturation current. Okay, this is mainly due to the minority charge carriers that is present in the diode. Fine. So if we want to summarize, how can we summarize? Okay, so how the ideal diode will, so for ideal diode, this is the VI characteristic. If I consider the voltage drop in the diode, this will be the voltage VI characteristics. If I consider the voltage drop the diode, voltage drop in the diode plus the internal resistance, the VI characteristic will look like this. Okay, so and now if we even consider the reverse saturation current, the VI characteristic will look like this. Okay, this is the ideal diode. Basically all these three are practical diodes. This diagram 1 is considering only the voltage drop. Diagram 2 is considering voltage drop plus internal resistance R, and this is considering voltage drop plus internal resistance plus reverse saturation current. Okay, okay, so this was all about diode for now. Okay, so now I hope that the characteristics of a diode is now clear. So now next we can move over to applications of diode. So we will start with half wave rectifier. So half wave rectifier is one of the most utilized application of the diode. Okay.